Hello, everyone, and thank you for joining us today. Welcome to Megger's Virtual Relay BPS. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentations and supporting you on any technical issues or questions for our presenter. On the bottom of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I'll read the questions out during the Q&A segment at the end of each presentation. Today, we will have two separate presentations with their own Q&A sessions, so please stick around after our first presentation concludes. Our presenter for the first segment today is Sughosh Kuber, Relay Applications Engineer. Also to assist with the question and answer session, we will have three panelists joining us today from our Protective Relay department. Mohit Sharma, Relay Software Applications Engineer, Abel Gonzalez, Relay Applications Engineer, and Marius Pitzer, Product Manager. Okay, let's go ahead and get started. Thanks again for joining us today.
Thank you, Michael. Good afternoon, everyone. I hope everyone is doing well and staying safe. Today, I'll be talking to you about transformer differential protection, and we'll also talk about the testing aspect, the testing of a differential relay. So here is the agenda for today. I'll talk about the current differential, the concept behind current differential, how does it work, on what principle, and then we'll talk about what are some of the challenges that we come across, either when you're designing settings for differential or if you're testing a differential relay, what kind of challenges do we face, and we'll also discuss the solution for those challenges. And then I'll show you the test setup and connections today that I'll be testing a differential relay using the Megger test equipment. And I'll walk you through each test in the differential protection scheme as to how we will test it in Rtms. So current differential, the number 87, that's the ANSI or the IEEE nomenclature to designate the differential protection, right? So Kirchhoff's current law. The law states that the sum of the currents into a node must be equal to 0, right? So the current differential principle works on this very law here. So if you look at this diagram here, the currents that is entering this node should be equal to the currents that is leaving this node, right? If there is difference on this side versus the side that the currents are leaving on, you would see difference in currents from one side to the other. In that case, we can say that the differential condition exists. So current differential works on this principle. So in this example here, I have a transformer shown with the CTs on both the sides. Obviously, the CTs are giving you the information to the relay, the currents information. And then I have considered an external fault. So the zone of differential protection is defined by the location of these two CTs here. So anything that is in between these two CTs is said to be within the zone of protection. So as we can see that the fault is external to my zone of protection, right? But how does the relay decide that this fault is an external fault? So, let's assume that the source is on the CT1 side. So you can see that the current is flowing in this direction from on the winding 1 as well as on the winding 2. And let's assume that these two CTs are compensated for the ratio mismatch and they're proportional on both the sides. So the differential relay consists of restraint windings and operate windings. So the operate quantity, that is nothing but the differential current in your zone of protection. So when you see a difference of currents on either side, you would see that there will be a current in the operate coil. And when that exceeds a set point in the relay will trip on differential. So ideally in this case, because they are balanced on both the sides and the fault is external, there will be no current flow on the operate coil, ideally, and then the relay will restrain from tripping on differential. And this type of relay, it works on the principle of percentage restraint characteristic. Now let us look into an example of an internal fault. So obviously you see that the fault is present within my zone of differential protection. We consider it as an internal fault. So we can see that the current on the winding 2, the direction is changed now because it's feeding into the fault. So which means that my currents on winding 1 and winding 2 are not proportional to each other, which means the currents add up such that I will see a current in the operate coil. And when this current goes higher than a set value, which is a relay pickup value, the relay trips on differential. So when we talk about differential protection, we talk about something called a slope characteristic, right? So what is this slope? Let us take a look at this equation here. I operate, which is your current in your operate coil, that should be greater than a factor of K with respect to your I restraint. So these quantities are calculated here. So this is your I operate and your I restraint, and these quantities are calculated based on the currents that is being read from the CTs on both the sides from the relay. So the moment the ratio of my operate with respect to restraint goes beyond the factor of K, the differential relay trips. And this K factor is what is called as your slope setting or slope characteristic. So one important thing to note here is that these equations you see here, they vary from manufacturer to manufacturer, and sometimes even within the same manufacturer, even within different models, you would see different restraint equations. Here we have a 3-phase differential scheme set up. It's a delta Y transformer, and you see that I have all the 3 phases connected onto the relay on both the sides. So the 3-phase differential uses the same concept that we just discussed in the single phase examples. Only thing you would see here extra is that you would see multiple operate and multiple restraint coils for each phase. So now that we have discussed about the basics of current differential as to how the differential relay works and operates, let us get into the challenges that we usually face in working with the differential. So the first challenge is CT mismatch errors. We have most of the times we will have different CT ratios on both the sides, right? So we need to come up with the tap settings that matches with the CT ratios we have on both the sides. So let us take a look at this example. I have an electromechanical relay nameplate that is shown here in the picture. And if you see here, it says it's current transformer ratio matching taps. So all these numbers you see here are options for you to choose the tap setting for this relay. And in my example here, the screws are on the tap 5. So for both winding 1 and winding 2. Okay. So with that given, let us look into an example calculation. So I have a 50 MVA transformer, and then 110 kV on the primary, 33 kV on the secondary. So when we calculate the primary and the secondary currents for the nominal load, we're going to get these numbers: 454 amps and 1515 amps. So based on these numbers, we're going to assume that we're selecting these CTs here, the 500 to 5 CT on the primary and 1600 to 5 CT on the secondary. So with all this information, let us see what will the relay read for my nominal current on the primary. What will the relay read as a secondary current, right? So for the winding 1 current, we will read 4.54 amps, and for winding 2, it's 4.7 amps. So if you look at the tab setting here, the closest tab that I can use for both the values is 4.6, right? If I select 4.6 as my tab, of course, they are not same as what I calculated them for. So you will see a 4.13% mismatch. So how can we address this mismatch that we are seeing, right? On electromechanical relays, the best thing we could do is obviously just selecting the most appropriate tabs to overcome this challenge. On microprocessor relays, it does mathematical calculations for the tap based on some input information, and then it calculates that to almost 100% accuracy with respect to your CT ratio mismatch. So here is an example equation for my tap calculation, wherein it uses all this information like MVA and voltage for that particular winding, CT ratio, and a constant. So this way, microprocessor relays can actually have an option to choose these taps that we want. For instance, the 4.54 and 4.73 can be the same taps can be used on a microprocessor relay, unlike an electromechanical. And that is how we overcome that particular challenge. And again, these calculations they differ from manufacturer to manufacturer. They have their own methodologies to come up with these tap settings. So phase shift due to winding configuration is the next challenge. So what I have here is a transformer with delta connected primary and a Y connected winding on the secondary. This means that there will be a phase shift between the quantities on one side to the quantities on the other, right? Because we have a delta Y connection here. So obviously the relay will see a difference in currents because of the phase shifts, and unless we tell the relay or we make the relay understand that we are working with a delta Y connection or a particular type of transformer connection. So understanding this challenge, understanding how to overcome these challenges will also help us when we are troubleshooting the relay settings. So let me talk about a bit about how do we see that phase shift when we are working with different transformer configurations. Here I have a Y connected or the star connected diagram here, shows VA, VP, and VC. And if I have to calculate VAB or VAC, let us look what happens, right? So VAB is equal to VA minus VB, and I'm assuming here VA or VB as VM because the magnitudes will be same and the phase angles are 120 degrees apart from each other. So you would get these equations here, and it results in this equation in rectangular form. When I convert that to the polar form, you would see this result, which states that the VAB is equal to the VA, but there is a factor of √3, and also there's a 30-degree phase shift between the VAB and the VA. And the same concept obviously applies for your current quantities as well. So it's important that we make sure that this is compensated in the relay or in the system. So for electromechanical relays, what we could do is we can work with the CT connection type. So we can use the CT connection as a delta on the Y side of the transformer and vice versa. So what this will do is the delta effect on CTs and windings of the transformer will have 30-degree effect coming on both the sides because we have used those type of CT connections. And this 30-degree effect will compensate for each other, and there will be no current in the operate coil because of the phase differences, right? They are compensated now. And this is how we can take care of this challenge when dealing with electromechanical relays. And this is the only way you can work this out. For microprocessor relays, of course, there are two methods. The first one is same as what we discussed now. We can work with the CT connection types. And another method is that microprocessor relay performs mathematical calculations inside the relay, and it actually addresses this phase shift problem. So that is called as internal compensation. What it does is that there are compensation matrices that are defined with respect to certain winding configuration. And based on what winding configuration we use, we can choose the appropriate compensation matrix to compensate internally inside the relay, and that is done mathematically. And when we do the compensation using the CT connection type, it's external to the relay, so it's called as external compensation. So if you look at this picture here, I have a delta Y transformer, but I have a Y connected CTs on both the sides. which means I have to perform this magnitude of √3 correction and angle compensation on both the sides internal to the relay. So let us take a look as to how those compensations are done. So in this example, I have a delta Y transformer with the delta on the high side and Y on the low side. But look at the CT connections here. It's Y on the delta side and delta on the Y side. So let's start with the currents that is coming out of the transformer winding. So these are the currents you see on both the windings. These are the A phase currents that is out of the transformer winding. So as you can clearly see that there is a phase shift that is created due to delta Y transformer type. But the CTs are obviously connected in the opposite type, which is Y and delta on the high and low respectively. So what happens is the currents that is coming out of your CTs to the relay are now compensated, which means the relay does not need to perform any internal compensation. So the CT connections actually helped us to take care of this challenge. So here, let us look when we need to perform an internal compensation. I have delta on the low side, Y on the high side, but look at the CT connections. They are Y connected on both high and low sides. So what happens is after the CTs, the currents coming from the CTs to the relay, this is how the winding 1 and 2 phase A currents look like. So if you see, this is a YD7. And when you multiply the 7 with the 30-degree increments, you see that there's a 210 degrees compensation that is needed, which I need in a counterclockwise direction so that my phase shift is taken care of. So when we use the right compensation matrix inside the relay, the phases are now compensated for, and then relay uses these currents and these phase angles to in the differential logic. So these methodologies vary from manufacturer to manufacturer. For instance, one of the manufacturers uses the numbers from 0 to 12 that actually corresponds to a 30-degree increment, which means if I have a number of 1, it's 1 30-degree increment. If I have a number of 2, it's a 60-degree total, because there are 2 30-degree increments. And that needs to be rotated in counterclockwise direction, and it will be corrected back to 0 degrees like we saw in the previous example. And different manufacturers have different styles of working with these compensation techniques. You just have to be wary about what kind of relay you're dealing with. You check the restraint equations, you check the methodology used to decide on the differential logic. So the next challenge is the zero sequence currents. So, zero sequence currents are present in the power system when we have unbalanced fault. Like here is an example of unbalanced fault, and any unbalanced fault can be resolved into 3 balanced vectors, positive sequence, negative, and zero sequence components. Now, using the symmetrical components, it's always helpful to analyze unbalanced faults. Today, I will not be talking too much about the symmetrical components. Rather, I'll be only focusing on the zero sequence current. So what are some of the properties of zero sequence currents? Those are obviously present during ground faults in the system. And another property is that these currents get trapped in delta winding as circulating current. So with these 2 properties, let's examine how it can create issues for the differential protection scheme. Here in this picture, I have a delta Y transformer, and I have Y connected CTs on both the sides. And then let us say I have a fault here on A phase only. It's a single line to ground fault. And then you would have a zero sequence current on the secondary side of the circuit. But on the primary, there would be no zero sequence current, because remember, we just discussed that the property of zero sequence is to get trapped in the delta winding. So what happens is that the primary side will not produce any zero sequence current on the line side. So because of that, the relay will see zero sequence on one side and not on the other side, for which it will think that I'm looking at a differential condition. But we don't want the differential relay to trip for this condition because this is an external fault. This is not within the zone of protection for my differential. So we need to make the relay understand as to how we can eliminate zero sequence, right? So let us take a look as to how we can work with the elimination of zero sequence. So the easiest way to eliminate zero sequence is, again, utilizing the right type of CT connections or ideal CT connection types based on your transformer configuration. You would connect a delta connected CT on the Y side and vice versa. So that will eliminate the zero sequence currents coming into the relay. In microprocessor relays, we have an option to utilize the compensation matrices like we discussed for the phase shift challenge as well. So utilizing this, the microprocessor relay performs mathematical calculations and it removes them numerically. And again, these matrices are numbered from 1 to 12. So let us take a look at an example as to how this is removed mathematically. So this is an example of compensation matrix number 1. It's a CTC1, and it represents the delta winding. So I have a 1/√3 factor here multiplied with my matrix, and I'm using that compensation matrix with the currents that is being fed into the relay by the CTs. So by doing that, I'm going to get these three equations. And when I use the equation in the form of symmetrical components, as you can see, I've utilized positive, negative, and zero sequence components to represent my currents. You see that my zero sequence components, which is represented by IO here, is canceling itself out in all the three equations here. So by using the right compensation matrix, I have numerically eliminated the zero sequence components present in my currents that the relay is utilizing to decide on differential tripping. Now we have eliminated this only numerically. The zero sequence currents are still present in your system. We are only telling the relay how to ignore the zero sequence this way. So the next challenge is a tap changer. Tap changer is a mechanism in transformer that allows for variable turn ratios in discrete steps. Here is a nameplate for a transformer that shows your voltage range for your tap changer, and along with that, the currents at that particular voltage level. So for instance, if I look at this voltage, 13,716 volts, I have an amperage of 1263 amps. Similarly, at the other end of my spectrum, I have 12,470 volts, for which I will be having 1389 amps. You see here, we have different currents for different voltage levels, obviously. So, if there are like no load tap changers, and if there is a change in the tap, the relay engineers have to make sure that they consider the whole range to be included when they design the differential protection. So even though there's a change of tap, that is actually taken care of in the tap compensation, right? So we can have up to 10% of mismatch on load tap changers, the on-load tap changers, and about 5% mismatch on the no-load tap changers. So what we can do to eliminate this challenge is that relay engineers, they use something called as percentage restraint characteristic. So additional slope can be provided in this characteristic, and this additional margin helps us for the allowance of maximum tap difference from the nominal in your slope setting. And we'll be discussing in detail about the slope characteristic in the next upcoming few slides. And obviously, if some of the relays, they may have tap position as inputs coming into them. So they can dynamically change these errors by adjusting your mismatch factor by using what voltage is being set at that particular time. CT saturation. Yeah, we have come across this many times in our careers, usually, in the protection field especially. So the CT saturation, when it happens, we know that the secondary current is no more linear to the primary current, right? So what happens is that obviously the transformer diff relay is going to see a difference of currents because the CT is saturated and the currents are not same on both the sides because of the saturation. And then it will result in an operational differential. But we don't want the differential to trip in this condition because this is not an internal fault condition. Differential is designed to operate only for the internal faults. So we can have different types of CT saturation. When we have symmetrical faults present, we will have some odd harmonics and some AC components present in those type of saturation. The severe type of saturation is caused by the asymmetrical faults, which has both AC and DC components. This image here is taken from a C37 standard. If you look closely, we have the waveforms for the primary and secondary both here. And because of the CT saturation, we can clearly see that the secondary waveform is distorted as compared to the primary. And if you consider the RMS value on both the sides, the relay is going to see a difference of currents and trip on differential. But again, we don't want it to trip on differential. So let's see how we can solve this problem. Here I have a pictorial representation of slope characteristics where I have the restrained current on x-axis and operate current on y-axis. So this lines you see here is nothing but your slope characteristic or the restraint characteristic. So the first line you see here is your pickup point for your differential relay. And the second line you see here is your slope 1, followed by a second slope and an unrestrained pickup. So based on the currents that the relay receives, it's going to calculate the restrained current and an operating current and puts that calculated plot on this characteristic here. So if my plot falls below this characteristic, it is called as a restrained region. The relay will be restraining and not tripping. The moment the plot goes above my slope or this characteristic, it will be in the operate region. Okay. So now let us take a look at how these different regions are used to overcome some of these errors. So region 1 and 2 here are used for steady state and proportional error compensation. Like we just discussed some of the challenges like tap mismatch, or you have low tap changer issues, or there can be some measurement errors from relays. So when you add up these percentages that you want to provide as margin, you come up with a setting of somewhere around 30 to 35% for slope 1. Excuse me. And these numbers are used from IEEE C37.91 standard, and these are some typical settings. Of course, you can have a slope setting of 25 as well, just depends on your system and how you set them up. So slope 1, until this point, we are taking care of your steady state and proportional errors. But the CT saturation that we discussed in the last slide is transient in nature, right? It's a transient error, and it is giving us a false differential current. So for that, we are utilizing the slope 2, which is having a higher setting of around 60 to 70%. Remember that the plot on this particular characteristic is decided by the currents that we are reading from the CTs. So when it falls on region 3 here, our currents are way too higher to be even in this region, and the slope 2 will make sure that the differential is restraining even when my CT is saturated. And finally, the unrestrained pickup is a setting which is used for internal faults that are very high in magnitude. Here is a pictorial representation of how those margins of errors are provided for each type of steady state errors here. This was taken from one of the technical papers that was presented in one of the protective relay conferences. So the next challenge is magnetizing inrush. When a transformer is energized, it will draw really heavy current to energize its core. So this current is called as magnetizing inrush, and it's very high in magnitude. It's transient in nature. So what happens when magnetizing inrush current is seen is that it's only seen on the primary side, and the secondary side obviously would not have that current. So the relay will think that it's seeing a differential condition. So we can have magnetizing inrush for different scenarios, like when we de-energize a transformer and we are freshly energizing the transformer up, you will see a magnetizing inrush. Whenever there is a voltage recovery after the fault has cleared, the transformer is energized, and then you will see a type of inrush that will be your magnetizing inrush. And then another scenario is when you have multiple transformers that are in parallel configuration and you're energizing a parallel transformer, you can see magnetizing inrush currents. So do we want the differential to trip on magnetizing inrush? We don't want it to trip because it's a normal condition. We are only energizing a transformer and it's not a fault condition. If you look at this particular picture here, the inrush current is usually of high magnitude, like you see here. It's usually more than, it can be more than internal fault current sometimes, and because of which the differential relay will think that it's a differential current. And again, this inrush current can depend on a lot of factors as to when we are switching, as to what point on the wave that we are switching, and how much residual flux remains in the core. All these different factors can impact this magnetizing inrush. So let us see how we can overcome this challenge and tell the differential relay that when we energize a transformer, it's not supposed to be tripping on differential, right? So when current waveforms during inrush were examined, it was discovered that these currents are rich in second and fourth harmonics. So relay designers, they came up with a method called as harmonic restraint or harmonic blocking method. If I consider 15% as an example, so I take my 15% of harmonic ratio with my fundamental waveform. When that calculation goes beyond a setting, then the relay blocks my differential operation, which means anytime my harmonic content in the currents is 15% or more compared to the fundamental waveform, it's going to block the differential, because thinking that it's the time when the transformer is just being energized and nothing wrong is happening. So electromechanical relays are filter circuits that detect harmonics, and microprocessors they look for these inrush conditions based on the logic that is presented here. There can be some special cases as well when harmonics are being detected. You can have higher harmonics on only one of the phases and not on all the phases. And in microprocessor relays, you can have individual phase tripping for the differential. So in that instance, they came up with this techniques called as cross-phase blocking and cross-phase averaging. So when there is a high content of harmonic in one of the phases, the other two phases are also blocked along with the three phases, so the differential does not trip on any of these harmonic contents. So the last type of challenge today that we're going to discuss is switching onto a fault. Let's say when we are switching the transformer up or energizing a transformer and an internal fault occurs, we know that the harmonic restraint that we just discussed could delay the tripping. Even though it's an internal fault, we have the harmonic content. So that is where this unrestrained pickup setting comes into picture. Usually the inrush currents are typically around 8 to 12 per unit. So you would usually see this pickup setting to be of very high. It can be 10 per unit or 12 per unit, depending on your transformer in the system. And if you have worked on electromechanical diff relays, you would remember that there is an instantaneous unit on those relays. And this unit is used for this very reason to a trip for high internal faults. So to summarize so far what we've discussed regarding the challenges, we learned that the microprocessor relays, they perform some mathematical calculations to eliminate zero sequence currents, to address the issues of phase shift because of different winding configurations, and also it helps with the CT mismatch challenge. We also learned that we can work with the CT connection type for electromechanical or microprocessor if we have that luxury to when we use the appropriate type of CT connections, we'll be able to address some of these issues. we also learned that in the slope characteristic, if we provide enough margin in the slope to take care to address these issues like saturation and tap changes and many other issues, that will help the differential logic. And then harmonic blocking techniques are used to address the magnetizing inrush condition, or when we are energizing a transformer, not to trip as a nuisance trip when we are energizing. And finally, the unrestrained pickup characteristic is used to trip for high internal faults. So with this background that we just learned today, we're going to move on to the testing part of the transformer diff relay. Here I have shown the products that Megger makes to test different types of relays. And here I'll be using Smrt 46D today to test the transformer diff relay, which is a SEL 787 relay. So in this picture, I'm showing the back terminals of the relay here, the back side of the relay where I have all the terminals where we make the connections. And then on the right side here, I'm showing the faceplate for those terminals, which tells us what each of these terminals are used for, right? So for instance, here it shows that it's a power block here, which means I'll be making my connections for the power on this particular block. Similarly, there are some output contacts present in this terminal block. So we can use any of these output contacts for testing. And if you look at the bottom of the screen here, we have the current inputs for winding 1 and winding 2, which means we'll be making connections on the bottom terminals on the relay today. So let us take a look at the actual connections that I've made today, right? So I have my relay and I have my SMRT test kit here. So the first connection we're going to make is that I connected my battery simulator, which will provide my control voltage to the power terminal on the relay, right? And next set of connections is that I'm utilizing my current channels, the 3 current channels that is in yellow color, that are connected to the winding 1 terminal on back of the relay. And next connection is that I'm utilizing the red colored channels, which is a voltage converted current channel. And yes, these are the current channels that can be used to provide currents to the winding 2 terminal on your relay. And the last connection is that I have a binary input that is connected to an output contact I'm using today to monitor for your output contact operation, right? So to quickly recap the connections, first I made my power connection, and then I made the winding 1 connection on the relay using the yellow colored current channels. And then I did my winding 2 connections using my red colored converted current channels. Finally, utilize the binary input for your output contacts. So now let us go to the software and work on the test part of it. So I'm going to turn on the battery simulator, which will power up your relay. And then the first thing we're going to do today is that we're going to pull the relay test plan from the software, Rtms software. So I'll navigate to the library. And because I'm working with the SEL 787, I'll navigate to the manufacturer and pull the relay test plan. And we'll load the settings. Now, the test plan is loaded here. However, we still have to get the right settings that we are using for the relay today, right? So the next step I'm going to perform is that read the actual settings on the relay. So here is the setting that is already present in the template, but we are going to read the settings from the relay, and it's a serial type of communication. So it will bring up this dialog where we have to make sure all this good information is correct, the COM port and baud rate, and we will read the settings from the relay. So the important part is that when we are connecting and trying to read the settings from the Rtms, we have to make sure that the COM port is freed up and is being only utilized by the software and not logged up by the relay software. Okay. And after the relay settings are read, the settings are mapped in my test plan such that the tests are already ready to go with the test values. Here we go. We have all the settings that was imported. It also shows what were the settings that were changed from the last time, right? So we'll go and take a look at these settings here. So if you look here, some of the settings are shown in red because they were updated from the last time that were present in the template. And if we look at the, if I look at my CT connection, it's a YY, and here are my tap information, my slope 1 and slope 2, and all that good information. So once we read the settings into the test plan, let us navigate to the test plan itself and look into how these settings were mapped onto my differential screen. So here is my list of tests that were generated in the test plan. And let us go ahead and look into the test screen here. So this is called as differential screen, right? And when the settings were read from the relay, the settings automatically mapped onto the screen here. The first part of the screen represents your transformer information. The second part of the screen represents your differential relay settings information. So here we have the high side information and the low side, the MVA, and the transformer connection type is selected based on the settings we received. And you see here, these tap settings should match what we see in the relay settings, okay? And one other important thing here is a single phase pickup factor. Here, these factors are automatically updated based on what settings we have. Remember that these factors change from manufacturer to manufacturer or model to model. We have to make sure that you choose the right single phase pickup factor when you perform single phase tests on differential. Now, let us look into some of the important settings that we will consider for today's testing. So here, the pickup is 0.3 per unit. Okay, you see that it's in per unit and not in amps, right? So that is one of the settings we'll be testing today. The second harmonic content is 15%. So we'll be testing that as well. We have a fifth harmonic content of 35% that we'll be testing too. And then finally, the slope characteristics information. So I have the restraint equation selected here. Again, remember, these will be different from manufacturer to manufacturer. And I have an unrestrained pickup value, which is high in magnitude. And I have a slope 1 setting here, slope 2 setting. And here is my breakpoint between slope 1 and slope 2, right? So once I have all this information, we will move on to the test screen. So before we move on, it's going to remind us that this is what we're using for the testing. We'll make sure that that's how we are connected, okay? So let us go ahead and start the first test. That is a stabilization test. So why do we need to run something called as stabilization test? The reason I do this test is that we are checking the metering on the relay when I inject normal current, normal load condition current to the relay, which means there is no differential condition. The currents are balanced on both the sides. And I need to make sure that what I'm injecting is what I'm reading on the relay. Okay, so it's opening up the HMI for your Schweitzer relay so that we can look at the metering data. So let's go back as to what we're injecting here. So based on my taps, this is what I'm injecting here: 6.2 amps on winding 1 and 4.3 on winding 2, right? And we expect these currents on the primary that I need to be reading on the relay with this phase angles. So if you look at the magnitude here, the 187 matches what I'm expecting and 1037. So the magnitude is good, and the phasors needs to be checked as well. The phasors should be 120 degrees apart from each other, and they look correct based on what we are injecting. There is no differential trip or anything like that. One other thing we need to check, I wanted to show you, is the differential metering. Remember, when I was explaining you the slope characteristic, I said that in the ideal condition, when there is no difference of currents, the operate will not see any value here, right? So I see a 0 here for my operate. So we make sure that all this is taken care of by doing the stabilization test, which means my connections are good to go. You can also update these values in here with the phase angles and also the magnitude just for your records. So the next test is timing test. So what we're doing in timing test is that I'm injecting a differential internal fault. It's like a go, no go test, right? I'm injecting a differential internal fault, and I want to see how quick my relay differential logic behaves or operates based on the current. So these are the measured times. So I'm just doing a timing test for the differential. So let's move on to the pickup test. So remember, when I was discussing the slope characteristic, I spoke about the restrained pickup value. There was a line before the slope 1 that was called as restrained pickup, right? Which is nothing but your 87 pickup value, which is 0.3 per unit. Right? So we are performing this test, the pickup test today, for the single phases. I mean, all the 3 phases, phase by phase, and also the 3 phase for both winding 1 and winding 2. So what we have here is that I have the pickup setting itself, the actual setting, and I have the pickup setting in per unit again, but this is ongoing metering data based on what we're injecting onto the relay. And here is your pickup in amperage, where per unit is converted into amps, and obviously the percentage error, and if a relay is passing or failing for that particular test. So I see that my pickup is 0.3, but we're injecting around 1.89 amps where my relay is tripping, right? So how do we make sure that my relay is tripping indeed at the right pickup value? So let us take a look as to how we are arriving at these test values. So I have 0.3 as my pickup value. So I multiply that with my tap value on the winding 1. So that gives me my test current value of 1.875, at which or after which my relay is supposed to be tripping. So if you see this value, as soon as it reaches close to 1.875, the relay is tripping. If you see here, all these values match this value here. And now we are performing the 3-phase test with the same currents. As soon as it goes close to 1.87 point, it tripped. Now we are moving on to the winding 2 test. So it's just that we are injecting the currents on winding 2 now, just to make sure that it is still going by with the pickup value and it's tripping rightly so. So we have the 0.3 as a per unit here. But if you look at the values here on winding 1 and winding 2, they seem to be different, right? So let us take a look as to how we arrived at the test values for winding 2. So I have a 0.3 as my per unit setting. So I multiply that with my tap setting of 4.32 on winding 2, right? But it says that my test current value is 1.296. Okay? So it's not matching where the relay is picking up right now. But if you remember on the differential screen, I showed the single phase pickup factor. Because we are performing a single phase pickup factor, and there is a factor of 1.732 that we used, I need to multiply that factor along with this calculation to arrive at the right test value. So 2.25 is where my relay is supposed to be tripping, or anything more than that, it's going to trip. If you look at these numbers, that matches to our calculation here. So what happened on winding 1? We did not have any multiplication done there with the calculation. That's because our single phase pickup factor was 1 there, and for winding 2 it's 1.732. Again, on the 3 phase, if you look, the currents are way too smaller compared to my single phase. So what it is that we don't use the single phase pickup factor for a 3-phase test, and that is why the current is about 0.3 times 4.32 is just about 1.29 or 1.3 for a 3-phase. So let's move on to the next test, which is the characteristic slope test. So we have already checked the pickup line here in the previous test. This time we are going to validate the slope 1 and slope 2. So I'm going to select a point on slope 1 and a point on slope 2, and we are going to run the slope tests. So what is going to happen is that it's going to keep the restraint as 2.2, but vary my winding 1 and winding 2 currents, or ramp them such that the operate current exceeds beyond my slope setting, right? So the moment my operate value exceeds beyond the slope, which means my ratio of my operate with respect to my restraint is equal to the slope setting or close, it's going to trip, which it did. So if I calculate this ratio here of my operate with respect to my restraint for slope 1, it's going to tell me that it tripped right at 25% of my slope, which is correct. Similarly, we are validating now the slope 2, which is around 50%. And slope 2 calculations will be different when compared to the slope 1. So the relay tripped on both of these points, which means we just validated the slope 1 and slope 2. You can have multiple points selected on these, and all those points will be listed in this table. Let's move on to the next test, which is a second harmonic block test. So the second harmonic block test is what we are doing is that we are injecting a current which is of the fundamental frequency, and then also another current that is of your second harmonic. For instance, we are performing a single phase test here for winding 1. So we are injecting a current on A phase at 4.37, but we are ramping the second harmonic content current to a point where we read close to 15%, which means let us look into calculations again. So we are starting from a higher value of harmonic content currents. If you see here, it's being ramped down. So let us take the first phase as example, 0.663. That's ratio with the fundamental current is 4.37. It gives me about 15%, right? That's where my relay tripped. So why is the relay tripping at this 15%? Like we discussed earlier during the magnetizing inrush slides, when there is the percentage harmonic content is more than the set point, the relay is supposed to restrain from tripping and the differential. So here I have the three-phase test that is going on, and it's the same kind of calculation. It's going to inject. Now it's going to inject 3 currents on all the phases, right, of 60 Hertz, and 3 more currents on the same phases at 120 Hertz. So the SMRT units have the capability to inject more current waveforms just utilizing single current channel. It can in fact inject up to 4 different frequency waveforms utilizing the same channel. So the test has moved on to the winding 2 now. Here my pickup value is 0.454. That's based on the calculation again. Let's take a look into this calculation. So it's the ratio between your harmonics with respect to your fundamentals. The moment my harmonic percentage goes close to the 15%, it's going to trip. And all these tests, you can perform just a 3-phase test or a single-phase test. It's your preference. You can pick and choose these tests that you're performing. You don't have to be performing all the tests, but it is recommended that you perform all these tests when you're doing the harmonic block. But you have the option to pick and choose if you don't want to run through all these tests from both winding 1 and winding 2. So finally, we are into the last test on the screen, which is a 3-phase test for a second harmonic. And you can also perform this test the other way, wherein you can actually ramp up the harmonic from an operate zone to no operate zone. Now, there are different methods you can utilize to perform these tests. Now I'm performing a 5th harmonic short test. The reason this is called a short test is that it's a go, no-go test. So which means I have a setting of 35% for my 5th harmonic, which means when I have a harmonic content of 40%, the differential will not operate. When I have a harmonic content of 30%, the differential will operate. Okay, so that is what we are doing here, is that for all the phases and the 3-phase, we are injecting a fundamental current and also a 5th harmonic current, wherein my content is 30%, the relay should operate, and for 40%, there is no operation. And again, you could pick and choose these tests. You can pick and choose this test depending on what you prefer for your test report. So in the second harmonic test, we were going from a no operate region to the operate region. We were kind of ramping. If you observe here, we are not ramping, but we are injecting the current straight away such that it falls in that percentage zone of 40 or 30%. So now we are moving on to our last test, which is the characteristic short test. So we already performed the characteristic test here, which we validated these lines here, but we also have the option to pick a few points in the operate region and the restraint region. So when I run my test, we'll know what the relay is behaving for these particular points. So for this point, which is in the operate zone, the relay tripped. For this particular point, the relay restrained and did not trip, and hence it's showing a pass value. And then these calculations are again the same, pretty much what we saw on the slope characteristic test before. Now let us take a look at the reporting. So here I have my report. Let me print this report in a PDF form so I can show you the complete detailed report. You can also have these reports saved in the Rtms file format, which is the PowerDB XML, or you can print in PDF format for your records. So let me open up the PDF here. So what I have here is that I have my relay settings that we read from the relay that is shown in the report. You can opt to remove these settings from the report and just have it on your Rtms screen as well. And we have the differential settings information that's shown here. We also have the transformer information. And as we ran each test, all that test information is present in the report with the pass or fail. And it also provides your characteristic slope picture for your setting. So this concludes my presentation. Now we can move on to the question and answer session.
All right, excellent. So just a gentle reminder to everyone, we do have one more segment after this Q&A, so please stay tuned. If you do have any questions, please submit them now into the Q&A box at the bottom of your screen. We have a few minutes to go over as many of them as possible, so let's jump right in. Our first question is going to be from Marius. Is the Rtms software compatible of automated testing by combining several elements into a single routine test and running only a single simulation?
Okay, thank you for the question. Sughosh, I don't know if you can just go to that one screen where you had the test that you just performed. Then I can probably explain better. There we go. So if you look at the screen that's up now, you can see that in this tree, it's defined by the test groups on the left-hand side, and then the different tests that will be performed on this specific relay. So this is done specifically, in this case, for the Schweitzer 787, but you can add some other groups into the test groups, and automatically it will be added some additional tests on the right-hand side. So if you look at there's a single play button in the right-hand corner, and then a double play below that. And the single play is to run one test that is highlighted, and the double play, you have different scenarios where you can run all the tests that is remaining, or some of the tests that hasn't passed. So you've got different options as far as running a simulation for a specific relay. And I hope this answered the question.
Thanks, Marius. The next one I'm going to throw over to Abel. Abel, which type of CTs classes are used for differential relay, i.e. PS class or 5P10, 5P20? Which CTs are better?
Hi. As with any question regarding CTs in protection schemes and protection systems, there is no single answer to that question. No CT is better for every application. You have to determine how much current that you're going to have in your normal operation and how much current that you're going to have for the faults that you're dealing with. It depends on the transformer, the size of the transformer, the system that you are connected to, etc. For instance, you're mentioning here two IEC classifications, the 5P10 and 5P20. They are CTs that guarantee a 5% error up to 10 times in the case of the 5P10 of the nominal secondary current, and the 5P20 is 5% error up to 20 times the secondary nominal current. But there's no mention there, for example, of which of the, I think it's like 10 classes of VAs that you have on the IEC standard. So again, the question is, do a study of your protection system, see if your CT is going to be adequate for that application by using the load that you're going to have connected to it and the excitation curve of the CT. And that would be the way to do a proper dimensioning of the CTs that you're going to use in that system.
All right, thank you. Mohit, next question is for you. How can we calculate the percent CT mismatch error for numerical relays?
Thanks, Michael, for the question. So the slide that Sughosh showed was explaining the electromechanical relay, and that's the reason there were a lot of calculations for CT mismatch, because in electromechanical relays, you have fixed steps. So if you're computing the CT secondary current and it is coming out in decimals, you have no way to select that value. All you have to select is a tap value. So either a 5 or a 4.6 or a 4.2, any one of them. Whereas in microprocessor and numerical world, you can actually put in the tap value as in the decimals. So you can go into like 3 points after the decimal and so forth, depending on the manufacturer. So there would be no CT mismatch error compensation required when you're using numerical relays, as you can put in the values exactly what the CT secondary output is.
All right, thank you. Marius, I have a question for you. Is the SEL787 also in the SMRT 410?
Sorry about that. Okay, so to start off with, the relay template does not sit in the actual test set. It's part of the software. So once you make the connection with the Rtms software to your test set, and in this case, if it's an SMRT 410, the software will recognize that you are using or that you are connected to an SMRT 410, and it'll adjust the parameters according to that. So once you get into the test module for the SEL787, that test will automatically adapt to the 410, and you'll use the 6 dedicated currents if it's a 5-channel box, and it'll automatically detect that, and then you can run your test with that. If it's going with an SMRT 46, then the 3 voltage channels will then have to be or will be converted to current channels to perform the same test.
All right. Sughosh, the next question's over to you. Can you go over the single phase pickup factor in more detail? How is it calculated, and what values can it be if not always square root?
That's a good question. So, and it's an important one, because let me go back to the differential screen here. So the single phase pickup factors, in this case, it depends on what kind of connections I have. So basically, these single phase pickup factors are nothing but your connection compensation that we are utilizing, because we are using this number in calculations when we perform the single phase pickup factor. Now these numbers, this may not be √3 all the time. It just depends on what kind of compensation we are even using in the relay settings. For instance, let me go back to the relay settings screen. And in the settings, if you look at our winding 1 and winding 2 CT compensation, we have 0 and 1. So all those single phase picker factors depends on what kind of compensations are we even using. I hope I answered that question.
All right. Mohit, can I connect my CT in deltas to phase shift compensation?
Yeah, that's absolutely, you can do that. Since we, in the back olden days, we had electromechanical relays, there was no way for providing a phase compensation using a setting. So in those days, they were using different CT connections to compensate for the phase shift. So yes, you can use different CT connections. Even in numerical relays, they give you options to choose the CT connection as Y or delta. So the answer is yes.
All right, thank you. Marius, can you show testing a transformer 87 with a single phase test set?
Okay, so in this presentation, we obviously did not accommodate testing differential with a single phase test set. But in the case of an SMRT1, which is the Megger single phase relay test set, you can convert the voltage channel to a current channel, and you can therefore do differential single phase. So one channel at a time. So you'll have two current channels available to do such a test.
All right, thank you. Abel, what is SOTF?
Sorry, okay. SOTF, that's switch onto fault. That's a type of protection that is used on a lot of systems, actually, that prevents the successful culmination of a closing operation when the relay or the protection system detects that the switching is being done and a fault is present in the system. There are several implementations of that protection function. I guess that should answer the question.
All right then. So Mohit, can I test REF and differential protection by SMRT using any automatic testing plan?
That's a really good question. I'm going to actually give you a brief intro on what REF is, because there were some questions popping up asking about what exactly is REF. And so I'm considering answering those questions in the same answer. Let me start with REF. REF is actually nothing but a technique for sensitive detection of ground faults in a grounded Y-connected transformer winding. So what it does is it employs 3 phase CTs on the phase side and a neutral CT. And by the name, it suggests that it's restricted for all the earth faults happening in that zone. It's nothing but a differential protection, but in the zone where you're considering the neutral CTs as well as the phase CTs. Now, the implementation in most of the relays is what I have seen so far is such that they utilize a directional element for comparing the current in the neutral, which they call as the zero sequence current, and comparing that with the current computed on the phase side. So they keep the computed zero sequence current on the phase side as a polarizing current, and then use the current flowing through the neutral CT as the operate current. So there is just a comparison between the polarizing and the neutral, like a directional element. And of course, we have ramp screens where we can use provide directional with one current source, and use the other sources for doing the operate quantity. So I mean, it will depend on how you're doing it. Either you can do single phase by providing just one current to the neutral CT, and then you connect the 3 phase CTs in the zero sequence fashion, and then give that to one of the currents on the test set. So you are using 2 current sources on the test set in that scenario. If you don't want to do that, you can use 3 current sources on the test set for the phase side CTs, and then 1 current source for the neutral CT, and then you can define that way. So right now we don't have an automated test plan, but it can be easily designed, and we are coming up with more and more modules. So the module would have full features. Like let's say if you are picking a cell 787 relay or a 587 relay, if that relay has a restricted earth fault element, then we would provide an automatic plan for that. So yeah, stay tuned. The modules are coming. Yeah, you should be seeing them in some time.
All right, thanks. So Marius, question for you. Can we put company logo in PDF test reports? Is it required to have premium software or basic software?
You can definitely change the company logos, and in this case, Sughosh has got the report up again. So because this is PDF, you can't do anything in PDF, but in the actual report screen on in Rtms, you can go to the tools menu. You can select the options on the left-hand side, the little, yep, right there, and you'll see that there's your logos for the left and the right. You can then go and browse different logos, whatever you want to put up, and that will then change the logos on the left side or the right side of your report.
Thanks a lot, Marius. Our next question is going to be over to Sughosh. Can I inject fundamental and 120 Hertz on the same channel for second harmonic blocking?
Yes, yes, that is what we performed when we did the second harmonic test. If I go back to my connections, here so when I was doing the A-phase harmonic test, I used this current channel. On this terminal, the same current channel was injecting two waveforms. One is your 60 Hertz and one is your 120 Hertz. Similarly, when I was doing a three-phase test, all these channels, all the three channels were having two waveforms each, one of the 60 Hertz and 120 Hertz.
Thanks, Sughosh. Mohit, will RTMS read settings from older GE Molten 745s? What test plan is used for the GE Molten 745?
Yeah, as I said, the modules, test plans, they are not out yet, but we do have the tools to read and create test plans. The 745 relay in general, it uses Modbus for communication. So we do have a feature of reading Modbus settings. So the answer is yes, we can read that. All you need to do is find the Modbus address, the slave address for the element, and you have if everybody is familiar with the Modbus communication protocol, all we need to do is we need to first map it in the software, and people can get in touch with me if they require training in understanding how we are reading Modbus, or any one of us, and we will be more than happy to help you out on that segment.
Thanks. Sughosh, the next question is for you. Why is your reading of 1.732 not considered in winding 1?
Okay, that's a good question. Going back to the RTMS, remember so the question is about a factor in my single phase pickup where 1.732 is used on one side, but it's not used on winding 1. So if we go to our settings, let us look into what kind of settings we have. That is, it's a delta Y transformer, right? But my CTs are YY, which means on the delta side, the CT is already connected the way we want it to be connected. There is no compensation needed on the winding 1 side. And that's why your compensation is also 0. And we have used 1 as the factor, which does not change our end value or the test value that we are calculating before injection. And that's why we have not considered any other value except 1 for winding 1 in this case. Hope I answered that question.
All right. So Mohit, next question's over to you. How does Megger software differentiate default settings that are not being used in the relay to reduce the amount of tests we have to run?
Okay, so we are in the mode of using scripts, the Visual Basic scripts, in defining which settings are enabled and which are not enabled. So in the scripts, what we are doing is in the background, if we are actually seeing the setting in the relay, if the setting is enabled, we would show that test to the user. If the setting is disabled, we would hide that test. So the user will not see that tests if the settings are disabled. So this kind of concept and philosophy is there in all our test modules that would be coming out soon.
All right, thanks. I think we have time for one last question, and it's going to be for Sughosh. Did you make any changes to the SEL 787 logic in the output contract?
Yes, I did, especially for the output contact I was using for the test today, which is out 107 or 103. I made sure that it had the term 87R, which is the restraint differential trip keyword in there before we started the testing. Yes, you have to make that change in the output.
All right, so it looks like that's the last of the questions we can answer today. If you ask questions we didn't get to them during this session, we're going to be reaching out to you in the next week or so offline. So we're going to jump out of Sughosh's presentation and go into Abel's. So as I said before, our second presenter this day is Abel Gonzalez, Relay Application Engineer. And in case you forgot recently, our panelists here to assist with the Q&A session are Mohit Sharma, Relay Software Applications Engineer, Marius Pitzer, Product Manager, and this time Sughosh Kuber, Applications Engineer. All right, we can go ahead and get started whenever you are ready, Abel.
Do you see my presenter view properly there?
Yep, we are in the right screen.
Okay. So just a preview what awaits. Okay, so this is going to be a webinar on understanding distance protection and testing distance relays. I'm going to be the presenter. Our panelists today are going to be Sughosh, who just presented on differential protection, and I'm going to have Mohit and Marius as well, who were panelists on the previous seminar as well. So as I said, it's understanding distance protection and testing distance relays. The agenda today is going to be, well, a small introduction, and then talk about why do we do distance protection. We're going to go over the impedance calculations required for distance protection and what are the compensation factors and how are they calculated. We're going to talk about the zones of protections used in distance protection. And we are going to discuss as distance protections characteristics, modes and quadrilaterals. Then we are going to talk about source impedance ratio, and we are going to finalize by testing a distance relay with Rtms. So as an introduction, I want to start with a statement. Here, I'm going to say that I have a line, and that line has a length, and my statement is that the impedance of the transmission line is a function of its length. We have equations. The first one that I'm showing here is taught, I think, in 8th grade or 7th grade physics, that tells you that the resistance of a conductor is proportional to its length, inversely proportional to the area, and also proportional to a quantity called the resistivity. And I can define the resistance per unit length of the line as R, as I did it there. I can also say that the inductance of the transmission line is proportional to its length, and of course the reactance, which depends on the inductance, is proportional to the length of the line. And here we have the reactance per unit length of the line. For those who don't remember their times studying electrical systems, GMD and GMR are defined on the side here as geometric mean distance and geometric mean radius. And in the end, we come to an equation where we have the impedance equal to the distance or the length of the line times the per unit impedance of the line. So we have just, proved that we can establish a direct relationship between, or a direct link between, the impedance of the line and its length. And this is very important because this is where the let's say, basis for distance protection lie. So let's say that I have this equation that I have just defined there. So I can say that if I know the impedance of a line, I can calculate its length, and the other way around. All I need to have is one in order to be able to determine the other. Now, does it mean that if I am somehow able to measure the voltage and the current that are circulating on the line at any given moment and calculate the impedance, I could tell the length of the line? Well, the answer to that question is not really. And you know why? Because typically when you have a transmission line or some sort of electrical line, most of the current that circulates on the line doesn't have to do with the impedance of the line itself. It has more to do with the impedance of or the amount of load that is being transferred through that line. But there are cases where you have that most of the current circulating on the line in that moment depends only on the impedance of the line. And when is that? Well, precisely in the moment when it matters most to us, which is when there is a fault. Because when there is a fault, we know that most of the current that will be circulating at that moment in the line is dependent directly on the fault and not on the load itself. At the moment of the fault, the amount of current circulating in the line because of the fault is most of the times much greater than the amount of current that's circulating because of the load. In some cases, the load can be neglected because the voltage at the point of the fault drops so much that impedes the transference of power through the line. And we can say here, we can use the, let me put my pointer up here. We can use this df, which would be the distance to the point of the fault, and we can calculate it as the voltage at the source in the moment of the fault divided by the current that's circulating through the line at that moment, right? So we know then that when we have voltage on a particular line and we have current circulating, if the current that's circulating is because of the load, typically we will have the locus of that, let's say, apparent impedance will be closer to the resistive axis in a resistive and reactive diagram here, because most of the load we try to make circulate most of the load in the form of active power. And therefore, we are going to have a low power factor when a lot of load is being transmitted. Now, when we have a fault, however, and since the impedance of lines is mostly dependent on the reactance of the line, and because of what I said before, that the current at the moment of the fault, because of the fault, is much greater than the current of the load, and that's one of the reasons why we have to protect against that, because the line is not designed to withstand that much current during a long period of time. Then what happens is that at the moment of the fault, the apparent impedance as measured here at M is going to jump. It's going to go from where it was before down here to where it is now, and it's going to become mostly reactive. So we're going to have a jump in the angle of the apparent impedance as measured at the point of measurement where we were before. We see that the calculation is very much the same. We are saying the impedance at the moment of the fault equals voltage divided by current. It's Ohm's law. And during load conditions, the impedance of the load equals, well, the voltage of the load divided by the current of the load, right? Now, is it that simple? No, we're gonna go over how to calculate the real impedances a little bit later. Now, before we go into the calculations, I think we can stop here and we can talk about why do we do impedance protection. First, yesterday there was a webinar that we had on overcurrent. For those who were not there, I recommend you guys go and find the recording and see it. And there, my colleague David Beer, he talked about the high levels of current that circulate on lines and how do you do the coordination on between different protection devices along the line when using the, let's say, time-based coordination and using only the current levels. Now, as we saw yesterday, for relays that are upstream, it makes it more difficult to coordinate because they have to wait for relays downstream to operate. So one of the reasons to have a distance-based instead of a current-based device is that it makes the coordination of those relays a lot easier. The second one is that the faults need to be cleared rapidly. We were talking before that, let's say, current-based coordination schemes or current time-based coordination schemes, they tend to be a little bit slower. With distance protection, we can detect and clear faults very rapidly. We have, with distance protection, fixed impedance reach. We will see what that means a little bit later. And I'm going to say something that is very important. The basis of all impedance protection is the fact that the impedance zones have fixed impedance reach. They are very sensitive. They are very easy to set. The calculations and coordination based on impedance are very simple to make and understand. And we can have fixed zones of protection that are relatively independent of system changes because they depend only on the impedance of the line that we are protecting and not on the amount of load that we are, well, not absolutely, but they're very independent of the amount of load that we are transferring. In the system, this is the last thing, that they have a greater independence of the load than other types of protection. So we have gone through, let's say, the basis, the justification. Now let's get a little bit, let's say, dirty with the mathematics behind impedance calculations. Don't be afraid. It's simple. Well, not simple, but it's not that hard to understand for those who have a little bit of a understanding on network calculations. Now, we have to understand one thing. The M that I have here is, let's say, the relay that is making the measurements on this protection system. It could be a relay, it could be anything that is measuring voltage and current at the same time. Now, we're talking about impedance calculation. Ohm's law tells us that in order to get impedance, you need both voltage and current. You divide them, you get impedance. You get some impedance. Now, all the impedance calculations are based on the location of the fault, where is the fault, and the type of fault. Why? We're going to see right now that for different types of faults, we're going to have different equivalent circuits, and therefore we're going to have different impedances for faults that happen on the same place. We have three-phase faults or ABC faults. We have face-to-face faults, AB, BC, and CA. And we have face-to-ground faults. A lot of relays out there use the 6 fault loops that we are mentioning here on the last 2 lines, AB, A to B, B to C, C to A, and AG, BG, and CG to make decisions on the type of fault that, that we have. For instance, if you have faults AB, BC, and CA, it means that you have an ABC fault. If you have face to ground, let's say an AG, and you don't have anything on the others, then it's a single face to ground. It's not that simple, and they run a lot of algorithms, but the idea is that they run a lot of relays out there. They run 6 loops, and the loops that they run are face to face and face to ground faults. Now, for a 3-phase fault, we have this network. The idea is that a fault happens here at this point. Now, for you to understand the circuits that come later, the impedance that I'm calling here ZAF is the impedance of the phase A to the fault, or between the measurement point here, the green is the relay where I'm measuring, to the fault. The impedance that I have behind that, that relay and all the way to the power source is what's called the impedance of the source, or the source impedance. That will be very important further on when we discuss the source impedance ratios for distance protection. So now the one thing that we have to notice about 3-phase faults, very easy to calculate. we can consider that the impedance to the fault of each of the phases is the same. They will therefore form a balanced system, and then the current here is very easy to calculate. It would be the voltage divided by the impedance of the phase, and therefore the impedance to the fault of the line equals directly the voltage divided by the current. Correct? So this is the simpler one. We can assume typically that during a three-phase fault, there is no neutral involved, and we can do the calculation right here. Remember, we can use the equations that we showed before to calculate or estimate in some form the distance to the fault. Even if we don't know how far it is, we do know how much impedance there is, and that's the very important concept, and that's why they're called impedance relays. Now, a face-to-face fault is a little bit different. In a face-to-face fault, again, the neutral is not involved. We don't have anything going on phase C. The phase C could have its own load going on. I don't know what's happening on phase C, but on the other two, we have a current going from A and coming from B, which means that these two currents have the same magnitude, but they are 180 degrees apart. And we can say that the current that circulates in this circuit is voltage here minus voltage here, which is the line-to-line voltage, A to B, divided by twice the impedance of the path. That's why the equation to calculate the impedance for a face-to-face fault has these two that did not show on the previous equation for the three-phase fault. And for the case of the phase-to-ground fault, now this one is a little bit different because now we have only one phase. We have current circulating through the ground, and these equations apply. Now, the problem is that I'm only interested in how much impedance do I have to the fault from the measurement device to the fault. But I have, let's say, a parasite impedance here, which is the neutral impedance that shows up and that I cannot take away from the calculation. And if you use only the voltage here and the current to do the calculation, then you will get that the voltage divided by the current equals this impedance plus this one. And this is why faults occurring on the neutral are a little bit more tricky, a little bit more difficult to estimate what the actual distance is. We are looking for this impedance, the impedance to the fault on the line, and we get this much impedance. We actually get the impedance of the ground loop, and the impedance that you know, it's external there and we don't want is the impedance of the neutral, but there's nothing we can do about it. It is present during the fault, so we have to learn how to deal with it. There are equations. In a previous presentation I did, I went through the painstaking process of developing the equations, but with a little bit of math magic, we can come to the conclusion that the impedance on the neutral equals this equation that I have here, and we call it the ground return or residual impedance. Now, see that the circuit that I have here is a sequence components circuit where I'm connecting in series the positive sequence, negative, and zero sequence networks, and I'm simply doing the math over this circuit. Why is this important? Because in every relay out there, you see that for ground faults, as they are called, the phase to ground fault, I call them phase to ground faults, or in most of the literature, they call them ground faults. You have this compensation factors. And what the compensation factors do is they deal with the fact that in a single phase to ground fault, there is an amount of impedance that has nothing to do with the impedance that I'm looking for. And the way to deal with it is by calculating a type, let's say a type of compensation factor. There are several types of compensation factors. I'm going to mention 4 here. This one's called residual compensation factor, and it's used like this to derive the impedance to the fault on the line. Remember, this is the one that we are looking for, and we can calculate it by using this compensation factor, and this compensation factor is a function of the zero sequence impedance, the positive sequence impedance, of the zero sequence and the positive sequence impedance of the line. There is another one called zero sequence compensation factor, and there are some others that are called earth impedance or residual compensation factor. They're all used, let's say, the same way. Now, different relays will have different compensation factors, and the idea is that you have to learn how to use them in order to, and you have to understand what those compensation factors. Now, I'm going to show you here a diagram that, in my opinion, connects what the compensation factor means and what it means for our impedance protection, and especially later for our impedance testing. See, this is the impedance to the fault, the impedance over the line to the fault, without considering the expansion that happens. See that this characteristic here expands when we have a fault to the ground, and we call this expanded impedance, we call it the loop impedance, right? Now, the loop impedance is the per phase impedance, which is this one here, times 1 plus the compensation factor, right? And what this multiplication does is it makes this, let's say, it makes this addition of this impedance here plus the neutral impedance. But since we don't know how much impedance is there in the neutral, but we do know the compensation factor for that line, it's easier to do it this way than to try and do it with an actual addition. So for different faults, you have the per phase characteristic and you have the loop characteristic. And the loop characteristic and the per phase characteristic, they connect, let's say, this way. And the equation that connects them is this equation over here. So you can get any per phase impedance, multiply it by the compensation factor, and it will give you the equivalent loop impedance. I hope I have been clear with this. This is very, let's say, interesting, but it's also very central to how we test ground protection systems. Now, once we know what the impedance to the fault is, can we use this criteria? If the impedance to the fault is smaller than the impedance to of the line, should I trip? That is the, let's say that is the question. And why? Because you have to use some criteria for tripping. You have to use something that comparison, like a peak of value that you use in an overcurrent, where you say, if my current is higher than this, then peak up. And after a few seconds, if I'm using a time over current, then trip. Or if I'm using an instantaneous, if the current is higher than this, then trip. Can we use this CRISP criteria? The answer to that lies in the fact that we have errors in the measurement system, and no measurement system is better than its primary transducers. And the primary transducers that we're using here for our measurement systems are CTs and PTs. Now, we know that CTs are not 100% accurate. At best, a protection CT at best can give you maybe a 3% accuracy at rated current. If it is a very good CT, it can give you a maybe 1.5% if it's classified as both metering and PT. But when it really matters, which is when I'm having the fault, the CT will typically, and I think that's something that Sughosh showed in his presentation, what happens when a CT saturates, that you get errors. Now, the most common relaying accuracy class for current transformers is the C designation. If we have, for example, a C800, that means that when the secondary voltage of that CT is 800 volts, it will be able to have a maximum of 10% error if the current circulating by it is 20 times the rated primary current. So what I'm trying to say is that when it matters most, the CTs are the less accurate. Of course, we can design the system so that the CT operates in a, let's say, less than, in a scenario that's not that adverse to it. But even then, we have errors that have to do with the types of primary sensors that we use. And we cannot get away from those errors. Therefore, we can never do this crisp. If the impedance that I calculated is lower than the impedance of the line, we can never use that. We have to use some sort of security factor. Now, with that security factor comes the concept of the zone of protection. Now, what are zones of protection? Since we have errors that we just talked and we just mentioned, so we design this system so that the main or the initial, let's say the critical, the fastest protection trips, but only at 80 to 90% of the length of the total length of the line. Now we define that because we don't know. There is a gray area for this protection because of the inaccuracies of the inherent in the measurement process, that we don't know exactly if we are here or we are somewhere, and we need to trip very fast. We don't have time to make a proper 100% assessment of the distance to the fault. That's done by different algorithms that respond in times that are longer than the times that we take to make this decision. So since there is a trade-off between accuracy and speed, so we sacrifice a little bit of accuracy in the name of tripping faster. So this zone called zone 1 is instantaneous, should not reach beyond the remote bus. It uses 10 to 20% as the safety factor. And of course, we have the inaccuracies that we just mentioned, which are the relay measurement inaccuracies, the current and potential transformer, because the relay itself can be inaccurate, current and potential transformer errors and transient behavior. Line impedance values can also be, you know, erroneously calculated. There is always some sort of error when we estimate the line. The line changes a little bit over time. So, and we have transients that occur if we are using capacitive voltage transformers, etc. So zone 1 is again to trip all the way to 80 to 90% of the length of the line or the impedance of the line, and it should trip as fast as possible. I am using instantaneous there. Remember that instantaneous only means with no intentional time delay. Now, zone 2 should be able to serve as backup of zone 1 and should also look beyond the line. So zone 2 is typically designed to operate around 120% of the line. It should trip at typically around 20 cycles. We had zone 1 tripping instantaneously. So this one does not need to trip instantaneously. It should give the relays on B and C time to see faults in their areas and their zone 1s of protection. But if that doesn't happen, then it should trip in typically around 20 cycles. The time on that protection should be enough for the operation of the zone 1 protection and the breaker B to operate. And it should not reach beyond D. Right? Now, we have a zone 1 at 80 to 90%. We have a zone 2, I'm sorry, we have a zone 1, which is instantaneous. Then we have a zone 2 around 120% and tripping around 20 cycles. Now, since in relays, there's almost no limits to, you know, what we can do. It's only the only limit I would say is your own imagination and creativity. So we can design also a zone 3, which is available in most relays out there. that will cover, it could cover all the way to the end of the adjacent line. It is going to trip slower. Now, the time here, I'm not mentioning any typical time. The time is going to be determined by coordination. The trademark is that it's not instantaneous, and it should provide enough time, like in zone 2, for the operation of everybody, and it should only operate as backup. Now, here I am showing a forward-looking zone 3. See that this zone is only operating, or should only operate, for faults ahead. Let's say that the load here moves in this direction from A to B. So this is the forward-looking direction for this relay. You could, and it's also typical, to have zone 3 looking behind the relay. Again, the times here should be longer than those determined by coordination, and it's also not instantaneous, and it should also give time for the relays that should be behind A to operate, but it should only trip for faults behind the relay where they are implemented. Now, we've come here to the realization that distance protection should be directional. In distance protection, it is very important to know the direction where the fault is happening. Okay, it should know that if the fault is happening here, it should know, oh, the fault is behind me. It should know if the fault is happening here, it should know, oh, the fault is ahead of me. And that's one of the reasons, and now we're going to talk about the distance protection characteristics, why the impedance relay itself is not, let's say, a very popular option, because the impedance relay, if we take a, let's say, naive impedance relay, we can see that this impedance relay is actually a relay that can operate for any direction. If you look at the characteristic, there is nothing in this relay preventing it for measurements where the resistance or the reactance are negative. You can have negative resistance. Remember that the positive or negative here depends on what? The direction of the current, right? So you could have operations for this relay in quadrants of the XR graph that we do not want operation on. This relay looks actually in both directions. So we need to do some sort of directional control on this relay in order to be able to use it effectively in distance protection systems. So now that we have this, let's say, directional control on the impedance relay, we see that this relay is directional again. We represented here a relay on C. Initially, it was a impedance relay, which was on C, but it was looking in both directions because there was no directional control. But now we have a relay in C that, since we have some sort of directional control, it looks in the proper direction. Now, these relays, to be honest, they are not very, let's say, popular. They are a good idea. It's a good tool to teach the impedance relays, but the most popular relays out there are the ones that I'm going to present right now, which are the Mo and quadrilaterals. Now, the Mo is this one that I'm showing right here. Now, the Mo has the characteristic, as in with the impedance relay, that if the fault happens outside, let's say, of the gray area, the relay should restrain. It should not operate. If the fault happens inside the gray area, the relay should operate. Now, this angle that I have here, that's called the maximum sensitivity line. In some relays, it will be called the maximum torque angle, depending on, well, it's still called maximum torque angle even in microprocessor relays. But the idea is that this is where the relay should have its maximum sensitivity, and this is actually the angle of the line that I'm trying to protect. And the relay location, as with the let's say impedance relay that we saw before, it's located at the origin of this coordinate graph. So the relay is here, it's looking ahead. Now the thing with mole relays is that because of their implementation, they are inherently directional. Now, for faults internal to the relay, you would have on mole relays that the angle between the operate and the polarizing signal is going to be lower. Actually greater than 90 degrees. But for external faults, you're going to have that angle is going to be lower than 90 degrees. And when you are on the characteristic, that angle is 90 degrees. Actually, the fact that that angle is 90 degrees when you are on the characteristic, and that this line here is the diameter of this characteristic, that's why this is a circular characteristic, because we have a let's say a right triangle here, and the only way to have a right triangle and this being the diameter is if the characteristic being built is that of a circle. I'm not gonna go deeper into how relay mole characteristics are built. It's very interesting. Initially, they were built using electromechanical principles, but now they're simply built using phase and magnitude comparators in relays. I want to go back to the characteristic to show again a very important thing. Now, the fact that inside, for faults that happen inside the characteristic, the relay should operate. Outside, the relay should restrain. Now, here I'm showing a line that shows where the load would be seen in this graph. If we have load that, now remember, the farther out we are with the load, the smaller the load is. Why? Because bigger load would mean higher current would mean lower impedance. Lower impedance means that, you know, the distance from the axis here or from the origin here is going to be smaller. There's a point where the load could get into the characteristic and you don't want to trip for the load. And that is called load encroachment. I don't have a particular discussion of load encroachment here. I only have an example of a mole characteristic with load blinders where I design this with a certain amount of load encroachment. And what some relays do is they simply turn a blind eye when faults happen in this area, or when you see currents happening in this area, so that there is no operation for the load. Of course, this is let's say an extreme case that I am building right here. We can have this mole relays with more than one zone. So far, we have only shown you here one zone, but you can extend this as much as you want to. Like in this case, 3 zones. In this case, I'm showing 3 zones forward-looking, and in this one, I'm showing the, let's say, the more common one with 2 zones forward-looking and 1 zone looking behind the relay. Now, another type of relay that is out there, and I mean, not a relay, because let's say another type of relay characteristics. Now, nowadays, most microprocessor relays, they have both the mole and the quad, and it's up to the relay engineer and the relay operations or the protection operations department on the utility or wherever you are to implement this or that. And there are applications where the quad is better and the mole is better. But the idea here is that the mole is built with 4 or more, let's say straight line, the quad is built with 4 or more. Now it's called quadrilateral because it has 4 sides, but you will see later that some quadrilaterals, like this one here, has those, it's actually not a quadrilateral anymore. It has more than 4 sides because it includes blinders and whatnot. But typically what you have here is you have a reactance over here. That's a maximum reactance reach. And then you have two resistive blinders, and the relay should operate when the fault happens inside and restrain when the fault happens outside. And the origin here is the place where the relay location is. Now, building it and configuring it is a little bit different, but testing it is very similar. Here I have examples of different tests configured for the quadrilateral and the MO. And the good thing is that for both the MO and the quadrilateral, the ground compensation concepts that we just discussed apply. And it depends on the relay manufacturer what type of ground compensation factor you are selecting. All right. And it's up to you to know that if the relay has ground compensation, then you have to properly configure, select the type of ground compensation. Remember, I mentioned several types on my presentation. There could be more out there because, you know, creativity is something that never stops. So, but the thing is, you have to be able to configure, or you have to remember to configure the ground compensation. Otherwise, maybe your three-phase faults and your phase-to-phase faults will operate properly, but the ground compensation is going to be problematic to test. MO versus quad, I just wanted to give you some pointers here. The MOs are inherently directional, and they use only one comparator. Remember, we can use either a phase or a magnitude comparator. They have poor resistive coverage near the reach point. This is something that I didn't show, but you can see it from the characteristic that depending on where the MO is, let's say, where the tilt of the MO goes, you have at some point your resistive coverage kind of stops. It doesn't protect for low resistance faults near the origin anymore. Unlike the quads, which you can actually configure how much of this length you want to be. That's called the resistive reach of the MO. Now, the fact that it has poor resistive coverage near the reach point means that it affects its ability to be used for short lines. And when used on long lines, it is more likely to have load encroachment issues. Now, you can use blinders for load encroachment, but it's up to you. Now, quad requires an explicit directional comparator. Now, the quad has four comparators. It has a directional comparator because it's not inherently directional like the MO is. It has a reactance comparators, and it have two resistant blinders. We saw that on the characteristic when we showed it. The resistive reach is an independent setting because you can set the resistive reach, how much you want to reach on the resistive axis. You can set it. It's an independent setting on the relay, which allows for a relatively constant reach and easier coordination with the load. Remember, the load comes on that side, and I can make it, you know, close to but not into the load. And the fact that the resistive reach is independent can cover large fault resistance, so it can be used for both short and long lines. But just remember, don't set the resistive reach too far. Now let's talk about source impedance ratio. Each of these introductory slides to each of the patterns that I'm covering, or the sections, has some sort of, let's say, summary of what we are going to cover. Now, what is source impedance ratio? Remember that we had the relay measuring here. This would be the voltage that the relay is using. Now, that voltage is actually a function of the voltage at the source, whatever the source is behind the relay, minus the current that's circulating, let's say, because of the fault, times the impedance of the source. Now, this is an abstraction. Unless you're connected directly to a generator, you cannot know what your source actually is. You have to do a network analysis, the Thevenin equivalent of your system, and calculate what your voltage source and your source impedance is. Fortunately for us, there are a lot of programs out there that can do the calculation for us. But the idea is that if you're in the presence of a high current because of a fault, and that's what happens when you have a fault, that you have a high current circulating, the voltage at the relay is going to be very affected because it's going to drop by as much as the product of the current circulating times the impedance of the source. And the bigger this impedance, or the higher the impedance of the source, the higher the voltage drop, and therefore the lower voltage I'm going to have here. That has a profound impact on impedance relays, because if the voltage at the relay drops too much, then there may not be a lot left for the relay to perform its operations properly. Remember that it has to use the voltage to calculate the impedance that we are measuring. So the source impedance ratio, it's nothing but the ratio of the source impedance divided by the line impedance, the line that we are protecting. To the relay, it is the ratio of the source impedance to the zone impedance setting. So we can have different SIRs for different zones. It is effectively a measure for the magnitude of the faulted loop voltage seen by the relay, because the higher the SIR, the less or the lower the faulted loop voltage is going to be. So for transmission lines that have SIR greater than 4, they're classified as short lines. Why is that the case? Because remember that there is a straight relationship, or a direct relationship between the impedance and the impedance of the line and the length of the line. The longer the line, the greater the impedance of the line is going to be, and therefore the smaller the SIR for a given source impedance, right? So we classify them as short when the source impedance ratio is greater than 4. We classify them as medium when the source impedance ratio is between 0.5 and 4. And then we classify them as long when the source impedance ratio is greater than 0.5. And this table here that comes from, I believe, the Segre standard, or I don't remember if it's on the Segre from the IEEE, honestly. We have this classification. I think this is the same on both. But keep something in mind. It's not the length of the line that we have to use as criterion for classification, because this is misleading. You could have lines that, given their characteristics, or you could have places where you have weak sources. Weak sources mean sources with a high impedance, where the classification could give you something even if the length of the line is long. This is only a classification that's done on the basis of the SIR and the SIR alone, not on the actual length of the line. It is a very useful classification because it allows us to know whether we are going to encounter issues with the protection, the types of protection that we are going to design for that system or not, given the type of line that we have. Now, for short lines, we know that the higher the SIR, the more complex the night protection is going to be with zone 1. It makes it more difficult for the relay to differentiate between an in-zone fault and an out-of-zone fault. The higher the SIR, remember, shorter line, the lower the restraining voltage. Remember, the voltage is going to drop more at the relay for an out-of-zone fault. Measurement errors are more pronounced. You have greater current and voltage transformer errors and CVT transients. We have mentioned those already. And in these cases, other types of protection like differential may be preferable. I have prepared a small slide here on what is recommended when you have a short line. It's recommended to use line differential, some sort of schemes, not direct stepped distance protection alone, or phase comparison schemes. For medium and long lines, you can use all of the above, and you can also use step distance protection or zones of protections, as we have discussed. Now, as a summary, because we are about to end the theoretical part, we have talked about why do we do distance protection. We talked about impedance calculations and compensation factors. I hope I didn't bore you a lot with that. We talked about zones of protections, and we did a brief introductions about the characteristics like Mo and quadrilaterals, and we also talked about the source impedance ratio. As references for this, and here are both the relevant standards and some references that I have used. Actually, I like to say that I used about 200 different references for these seminars, although this is like the second or third time that I talk about this topic, and I'm getting more and more into it. So, but the standards, there are a lot of IEEE and IEC and SIGRE documents. I recommend that you guys, if you're interested in this, go and find those documents, because they give you very clear and very good guidance on how to use it, why do you use it, the characteristics of the relays, how to test those relays, etc. So you can find these standards on our presentation. Now, the line of products that we have, I believe you have seen this slide if you have been with us for a couple of days, is this. I'm going to use one of this to do my, actually one of this to do my testing. I'm going to test a 411L, and I'm going to test only the Mo phase distance element for both, I'm sorry, the Mo distance element for both phase and ground. Here are the configurations. I have here the line, I have the reach for the Mo, the reach for the ground. I'm using the same, and here I have the time delays for those, and this is how it comes to, I mean, how it shows, how the relay shows the settings editor that we have on the relay. As connections, I'm going to use this for the currents. I'm going to use 3 of the 6 voltage current channels that I have available on this unit, and I am going to use 3 voltage channels as well. I am going to power up the relay using the auxiliary power that I have on this source, and I'm going to use binary input coming from the relay. So now I'm going to leave the presentation, and I'm going to connect with PowerDB. Right now, my relay is on and my source is also on. It has been on for the whole presentation. I hope it hasn't been an issue. I can't even hear it anymore. So the relay that I am going to test is an impedance relay. I am going to bring it up here. It's a 411L relay, and I am going to go ahead and import or read from the relay the settings. I'm going to use the, I think it's a 57600, and I'm going to log into the relay, and I should be bringing the settings from the relay. Now, I do this because it's easier. I don't have to, type in all the settings and whatnot. It's just a simpler procedure, I would say, for me. We can do this with most Schweitzer relays. I think if you guys were here for the previous presentation, you heard Mohit. Oh, I had a, okay, changed from values, has been copied to the clipboard. It told me that the settings have changed. I have a lot of settings. I have all the group settings here. For example, I can come back and change settings and do things if I want to. And I don't know, you can go over all the different settings groups here if you want to. This is my trip logic, and you can see that on the relay as well. Now, here I am going to simply, I changed from milliseconds to cycles. Remember, we had 0, 20, and 60. I don't know if you remember from the slide where we had the settings there. I have 0, 20, and 60. You can see it over here. And fault time in cycles is always a bit larger than the time for the actual trip on that zone. What I have here are the different types of control that I can use. I rather use constant current for this one, but I could use constant voltage. I could use constant source. Some relays, you can only test them with constant source. Any other type of testing will not be accepted by the relay. But in this case, and I'm going to use pulse ramping. I could use binary search, or I could use shots. I like the pulse ramping because you can see it when we are testing. It brings, it performs different faults along a line of test, and it allows you to kind of verify the dynamic behavior of the relay. If I go into my testing, this is called click on fault, and I can select several faults. I'm going to select 3, let's say. For this relay, I'm going to test a zone 1, a zone 2, and a zone 3. In this case, I'm going to use an A to B fault. And if I click here, I will be running the three faults one by one, starting by this one on zone 1. What it's doing is it's using this line here, and along this line, it's generating different faults, and each of these faults is taking or is being, let's say, injected for a time that is shorter than the time it takes to trip on zone 2, because if you see, all these faults are actually on zone 2, but since they happen for a time that's shorter than the time to trip on zone 2, then in zone 2 you shouldn't trip. Now in this case, I'm coming from the outside of the zone 2 characteristic, and I'm coming to the inside. All those are outside of the zone 2, or the reach of the zone 2 of this relay. And again, it's coming into the characteristic, into the zone 2. As soon as it reaches the border of the zone, it should trip. Sometimes you get a little bit of inaccuracy because of the step, or the size of the step that you're using. And now I'm testing the zone 3. We had a trip on zone 1, we had a trip on zone 2, and now we can do the trip on zone 3. I can select, if I want, I selected this type of line, but I could have clicked here and here, and I would be selecting a different let's say, direction of the fault. Typically, more relays, they are tuned to trip around the maximum sensitivity angle, and it's typical to test them at different angles around the maximum sensitivity angle, and that's what we are doing right here. I could have even chosen a type of selection where the software, I'm going to show you that for the next type of fault. Right here, I'm just waiting for a trip on the single, on zone 3. So now I'm about to finish this. So now I have my 3 results for zone 3. I could use more points. I'm simply going to go and select an ABC, and here I could choose the search mode, for example, to this type of search mode where lines will be drawn that always have their origin at the position where the relay is located. Remember that the relay is located at the origin of the diagram. So we could test something like this, and we could test, let's say, something like this, right? So if I go ahead and run those points, now I only clicked 3 times, but I have 5 points. Why? 5, because for each of these lines, I'm going to test these 2 points, one on zone 2 and one on zone 1. And for this one, I'm going to test one on zone 3. So for each of these lines, I'm going to test 2 points, and for this one, I'm going to test 1. This is a good way, because what we're doing here is that we are keeping the angle constant. See that the currents that we have on the left side, we have the phasor diagram corresponding to those faults. The angle of the currents is not changing. In this case, it's being kept constant, right? Now we are going to test the same thing for the second fault on zone 2, and now we're going to go for zone 3. See how, again, the angle is fixed. The angle of the fault is fixed at the angle that I selected when I initially did the click on fault. Down here, you can see that we are testing zone 3, that the selection is on secondary ohms, and that we are selecting a fault type ABC. Up here, you have the possibility to simulate a contact if you want. That's something that you do if you're doing a simulation, if you're not actually testing, or if for some reason the relay doesn't operate and you want to stop the testing, you can do simulate, or you can simply abort the test. In this case, I have my 5 points. If I select now the ground fault, I can go ahead and select 3 points, the same thing that we did before, and we can run it again. Now it's telling me that the configured test line to short points will cause the test voltage to exceed the nominal voltage. Now, why is that? Why does that happen? Well, it happens because I'm using constant current, and the impedance that the test set is going to inject is directly proportional to the voltage and inversely proportional to the current. So if I want to inject and the impedance is too big, then I may need a big amount of voltage. And why didn't I see this before? If I'm using, if you remember, I'm testing a ground element that has the same reach as the phase element. Well, the answer is that we have been affected by the zero sequence compensation factor. Remember that the zero sequence compensation factor creates an expansion of the zone. And since it creates an expansion of the zone, now we have here an impedance on zone 2 that is larger than the impedance that we had for zone 2 on the phase element. Why? Because we are not showing the phase compensated impedance. We are actually showing the loop impedance in this diagram for the ground fault. As before, we are keeping the test angle constant, and we are simply waiting for the fault to get to the inside of the zone, and we will see the tripping happening there. Now, these red lines that we have here have to do with the, let's say, tolerances that we chose on the test. I didn't change those tolerances. I believe they are set at 5%, but I would have to check that. We can do that and change them to make them more strict. And right now, I have finished my testing. I think I'm running about 2 minutes behind, but I want to show you the report that we generated. Now, in this report, I have initially the let's say identification. We could say that the substation is, I don't know, somewhere in Mexico, and the position is number 1, and the equipment is located in a yard, and the test status is incomplete. And why is it incomplete? Maybe because I didn't finish testing all my points, but I can see my, because I was testing actually a differential before this. I'm sorry about that. So that's what hasn't finished. But here we have all the test results that we just did. We can change the names of the test if we want. Maybe we want to change this to AB, I don't know, SEL 411L-2 for certification. I don't know. You can change the name of the fault. You can see there that we have the ABC, and also we have the A-type faults. On the relay, had I not been doing something with the test before you guys, before I started, I should have maybe turned the PowerDB off. I would have seen the test as completed, right? It's a good thing that it showed as incomplete. Now I can put there my name. And I'm done with the presentation.
All right, thanks a lot, Abel. So we have officially concluded with your presentation portion of your segment. We'll jump right in. But first, to those that are leaving, if you could, there's going to be a survey that pops up when you close the webinar. If you could take a few minutes to provide your feedback so we can continue to improve upon future webinars, that would be fantastic. On the survey, you will also find a field that will allow you to request a demo or a quote on any Megger products. So let's jump into the Q&A session. Our first question is going to be for Sughosh. Sughosh, is Mo characteristics used only for phase fault protection?
No, not necessarily. They can be used for any types of faults, pretty much face-to-face, single line to ground, or three-phase faults. Not just Mo characteristic for that fact. Different other characteristic that Abel mentioned, like quadrilateral, they can also be used for phase as well as ground faults.
All right, thanks. Marius, how many zones of distance protection can be tested in RTMS?
So part of the click on fault tool that Abel has gone through, there is the three different methods: the line to neutral, line to line, and three-phase fault. And within each of these, you can go up to 20 different zones, whether that being forward or reverse.
Thanks, Marius. Mohit, our next question is going to be for you. Can you do some relay logic testing with the RTMS software?
Yes, absolutely. You can do some logic testing with the RTMS software. We have a ramp screen that you can utilize, or we have state sequencer screen that you can use to do some kind of testing like that. We do provide 10 binary inputs on our Smrt 46 units, and we have 6 binary outputs. So you can program different output contact on the relay, some kind of logic testing like different word bits, and then have them on your binary inputs. And then you can use your binary outputs for providing some kind of input status to the relay. And then you can set up the whole scenario in your state sequence to look for any kind of trip happening. And then if that kind of, when I say trip, it means that any kind of output contact getting triggered, you can jump onto the next state, or you want to stay at the same state. So there are like wide range of possibilities that you can do. And Mike Ditmore yesterday showed you how we can use a state sequencer. But if you guys have the specific question on your logic, you can get in touch with us, and we would be willing to help you out on that. Thank you.
Thanks, Mohit. Sughosh, next question's for you. What is compensation factor and how does it relate to testing?
So yeah, it's very important for the compensation factor. The reason being that the ground distance protection, they're typically designed to be set based on positive sequence impedance to the fault for single line to ground faults, like Abel mentioned. And the impedance that is seen by the relay is a combination of positive, negative, and zero sequence impedances of the system. So we know that the positive and negative sequence impedance they're equal, but to each other in magnitude and angle. But zero sequence impedance may have a difference of magnitude and phase angle. So because of this, the distance protection relays, they need to employ the compensation factor, something like a zero sequence compensation or a residual compensation that Abel was explaining, that is needed to adjust the measured impedance to reflect the actual system impedance. And again, when we are testing these different type of fault simulations, we need to consider the compensation factors to inject the right type of test values.
Thanks. Next question is going to be from Marius. Is it possible to read the settings for different manufacturer distance relays in RTMS?
Okay, yes, within RTMS, and I think as previously mentioned by, I think it's either Abel or Sughosh today, we can read directly from Schweizer relays and of course Modbus relays. We can also import XRIO, and examples as ABB RL670 or Siemens 7SA632. And then, of course, we can import our own CSV files and Schweitzer RDB text files.
All right, Abel, what is meant by loop impedances?
Okay, I'm sorry, I was muted there. Well, the loop impedances is when you have a single phase to ground fault. Unlike when you have when you have a three-phase fault, the only impedance that you have is the impedance of the let's say of the line, right? And the loop that you have there is a loop that's made of the voltage and the impedance of the line, and you divide this voltage between this impedance and you have the current, because this point is the center point of a balanced resistance system, right? So you know, by knowing the voltages of the lines, you know the voltage of the phase, and the voltage of the phase divided by the impedance of the phase, you have that current, and that's your. So that would be the loop impedance for that type of fault. For the phase-to-phase fault, it's different. This would be the loop impedance for the phase-to-phase fault. And you see this number 2 here, it's because you have the impedance twice in the loop. Now the loop is this loop here. In the case of a ground fault, the loop encompasses the ground. So since the loop encompasses the ground and the current circulating is actually the current from the phase to the ground, then this loop is different. And since this loop is different and it doesn't include only the impedance of the fault as in the other 2 cases, then we have to do the compensation that we talked about. But the loop impedance in this case, and in the other 2 cases, the loop impedance equals the fault impedance, but in this case it doesn't, right? Well, in the case of the 2-phase fault, it's actually the loop impedance is actually twice the phase to the fault, but it's very easy. So, but in this case, we have to do this this compensation because the loop impedance includes the impedance of the ground. I hope that answers the question.
Abel, Mohit, could you please explain load encroachment?
Yeah, so I think Abel explained it really well in his presentation. Load encroachment, by definition, you can understand it. It's the load is encroaching into the characteristic. So if the load is encroaching into the characteristic, we don't want our distance protection to operate because it's a load condition and not an actual fault. So usually this can happen, and the relay manufacturers provide some kind of load encroachment blinders, typically different settings, so you can distinguish between your load settings versus your fault setting. So a rule of thumb is load, you can differentiate a load from a fault with the power factor. Usually loads have high power factor value, which would lead to a low X/R ratio. On the other hand, faults are more or less reactive in nature, and the X/R is quite high. So this is how the relay manufacturers also differentiate. And yeah, I think I hope I answered the question.
I think we did. Next question is going to be for Abel. Could you please explain the coordination between the different zones on slide 32?
Okay. Well, the coordination in this case is, let's say, of 2 kinds. We are doing coordination by the amount of impedance that we are allowing. In this case, 80 to 90% of the line for zone 1. And the other one is going to, oh, sorry. Give me I don't know what happened here. Just give me a second. Sorry about this. Okay, so zone 2 is actually going to pick up for each of the faults that happen for zone 1, but it's not going to trip. It's going to allow zone 1 to trip first. Zone 1 is supposed to trip faster. See here that it says instantaneous. Actually, in zone 1, in some relays, you can get sub-cycle operations, very, very fast operations. Now, zone 2, the coordination between zone 1 and zone 2 happens because I'm doing time coordination. It's better than with overcurrent because I am allowing a fixed amount of time, and I'm using the fact that I know how much impedance I can cover, and I know that I am covering at least until the end of the line. And this is why zone 2 is typically around 20 cycles. So the coordination happens let's say in 2 ways. 1, by the amount of impedance that I'm allowing for each of the zones. 2, by the amount of time that I'm allowing for each of the zones to trip. 1 is instantaneous. The second one takes around 20 cycles, which gives zone 1 time enough to trip, and zone 2 then will operate if zone 1 didn't operate, or if the fault wasn't seen by zone 1. I hope that explains that.
Thanks, Abel. We have one last question, and that's going to be from Marius. For distance protection, does SMRT have tools for power, test, swing, and out of step?
Okay, yes, we do. And maybe Abel can just go and follow with me. The first one is we've got a dedicated power swing module that's in the software where you can perform these the power swing test. And then of course we've got the power swing, or manual power swing that you can use. Abel's pointing out power swing and out of step. You can see that he highlighted the 2 options there. And then of course there is the other method in the home screen where you can use it from the fault calculator to do a manual power swing. I hope this is clear, and it's pretty easy to find in the software.
All right, thanks. Actually, we do have one more question I think we should answer. It's going to be for Abel. In your experience, if there are 2 lines back to back, will zone 2 of line 1 operate first, or zone 1 of line 2? Similarly, will zone 3 of line 1 operate first, or zone 2 of line 2?
Okay, okay, yes, I am. So, well, the answer here is, if you have a proper coordination study, the beauty of protection these days is that there are so many tools, electronic tools, simulation tools that you can use, and they're very, very, very accurate to properly coordinate this this protection. So remember that we are allowing 20 cycles for this zone to operate. It will operate, and this is I'm pointing here at zone 2. I don't know if you guys can see it. I'm pointing here at zone 2. So this zone will operate in around 20 cycles. Let's say it picks up a fault here. So I believe this is the scenario that you're talking, right? You have a relay A and relay C in back-to-back lines, and relay A will have a zone 2 that covers a piece of the zone 1 of relay C. It is only meant to operate as backup. And since it's only meant to operate as backup, it should give enough time for the zone 1 of relay C, which should trip in instantaneously or with no intentional time delay in maybe a couple of cycles. It should give enough time for the zone 1 of this relay to operate. So ideally it wouldn't. If it does, then you have a problem with your coordination, and you need to do some, I would say some studying, but a proper coordination study and a proper simulation of the conditions, which you can do prior to the configuration of your protection system, can address those issues.
All right, thanks again, Abel. It looks like that's all the time we have for questions. We apologize if we did not get to your question today, but we will be following up with you offline the following week. A copy of the presentations, along with a link to the video recording of the webinar, will be emailed to everyone in about a week. When you close out the webinar, a survey should pop up. This survey will include a field for you to request a quote or a demo if you're interested. But thank you all again for attending and have a great week.